Our next video is about solving exponential equations, and we're going to start using something called logarithms today. So there's a couple ones that we've done before in solving. Things like 5 to the x equals 25 to the 2x. We can get these things to be the same bases. So this is 5 squared to the 2x. And so we have 5 to the x equals 5 to the 4x. So x equals 4x, or 0 is 3x, x is 0. So we can solve this one. And then when we're looking at this next one, we got 6 to the power of 4x equals 216. Well, 216 is the power of 6, so 6 to the 4x equals 6 to the third. So the exponent of 4x must be equal to that exponent of 3, so x equals 3/4 as a power. Well, then we get this third one here. We have 5 to the x equals 49. So we're going to write which power of 5 that this is. It's not a power of 5. I mean, that means that, it's somewhere between 5 squared, which is 25, and 5 cubed, which is 125. So I know this is like 2 point something. Um, I could estimate it. I could try like some brute force of it. But what's going to happen is I'm going to write this knowing that this is the exponent that I can apply to 5 and get 49. And the way we do that is with logarithms. The purpose of logarithms are to represent exponents that we don't have clean integer results when we apply that exponent, or that the exponent itself is not a clean integer. So all logarithms are exponents. This exponent right up here can be written as a log, and we will write that exponent as a log shortly. They take a number from a certain base to create a certain result. For example, if you have a to the power of b equals c, that also means log base a of c is b. Well, this is exponential form, and this is logarithmic form. What this b equals log base a of c means is that b is an exponent because it is a log. All logs are exponents, and this is the exponent that takes a base of a and makes its result come c. So here I can write this as log. I'm going to keep the same base. The base is 5 of 49. That's what x is. X is the exponent that it takes to go from a base of 5 to become 49. This log means an exponent. So when we go double check it, it's going to look kind of weird to you. It's going to be 5 log base 5 of 49 equals 49. This is a true statement because this is 5 to the power of log base 5 of 49. Log is the exponent that takes 5 to become 49. So 5 is getting taken to whatever power it takes to bring 5 to 49. So that means we're going to get a result of 49. Now, if we can go ahead and practice some changing from exponential to log form. If we're going to rewrite something in log form, it's going to keep the exact same base that we had before. This base is 5, so this base is 5. By the way, when you write these, it's not like it's all on the same level. This would be bad. What's happening is this 5 is a subscript. So we have the log and the result, which is 2, are on the same level. This 5 is a base. This says log base 5 of 2 equals 3x. This log is that exponent that was bringing 5 to become 2. This is it here in logarithmic form. We can do the exact same thing by moving from logarithmic form to exponential form. We have this base being q. The base of the log and the base of the logarithm are always the same thing. So you have q, and q has to get taken to some power to get 7p. That power is 8 because the entire log is the exponent. In this case, it equals the exponent. So 8's our exponent. It comes to the result of 7p. Well, in this one here, log base 4 of 5 is x because, well, that's just the solution. We could write it in this form. We commonly will, especially if we don't have a calculator. I have a calculator that I could go take out and find the decimal value of this. It's going to boot up hopefully quicker. So we could go ahead and in math, most of you will have down here something called log base. And we want to do log base 4 of 5. So we just put 4 here, 5 here. And this gives us an approximation of what exponent would take to apply to 4 to become 5. If we do 4 to the power of that last answer, we get 5. Now, these decimal answers are like a approximation. They're not, and they're very useful though when you're trying to go ahead and solve real problems. It is better when you don't have a calculator to write it like this. This is actually an answer. Then we're going to go ahead and evaluate each of these. This is really important because it talks about the meaning of what a log is. Log base 2 of 8. It's saying what exponent can you apply to 2 to become 8? Log, log base 2 of 8. Exponent that you apply to 2 to become 8. That number is 3. Because 2 to the third is 8. Likewise, you have log base 11 of 121 is the power that you apply to 11 to get 121. That's 2. Then we have log base 7 of 1. It's what power can we apply to 7 to get 1? 7 to what power becomes 1? Well, things that become 1 after a power applied to them, they're getting the power of 0. 7 to the 0th power is 1. Well, likewise, over here, you got log base 25 of 125. We have to find what power you can put on 25 to get to 125. They both have bases of 5. Square rooting this 25 gets us to 5. And cubing that 5 gets us to 125, so you get 3 halves. Some people sometimes go say, I know that this result is 25 to some power is 125. And then some people choose to solve in ways similar to what we did earlier, to say, hey, we have 5 to the 2x equals 5 to the third. And then, hey, our 2x equals 3. And so x is 3 halves, and they get the same thing. But you can do it by just thinking about it logically in many situations. Here, log base 27 gets over of 1/3. That means we're applying some power to 27 to get 1/3. Well, to get to 3 from 27, you have to cube root it. Well, cube rooting is a 1/3 power. That would give you 3. But 27 to the negative 1/3 will reciprocate that. So you get negative 1/3 is the value of that logarithm. Well, likewise here, you get 1/4. It's going to get some power to become 64. We got to want to reciprocate that so it's just a 4. So you're going to have to do a negative power. The negative first would get you to 4. 1/4 to the negative first reciprocates, gets you to 4. Well, and if you cube this, you would then have 64. So the log base 1/4 of 64 is negative 3. We're going to go ahead and end with solving these two. Yeah, that'll be the end of that. So if we look at this one here on the left, we have 3 equals 7 to the power of 4x minus 5. Well, we can't get this in the same base. There's not like 3 squared is 7, 3 squared is 9. 7 and 3 do not have common bases. But we can go say log of 7, log base 7 of 3 equals 4x minus 5. Because 4x minus 5 is the exponent, here's the exponent, that it takes to apply to 7 to become 3. Now we can go ahead and solve. We add 5 to both sides. 5 plus log base 7 of 3 equals 4x. And so x equals 5 plus log base 7 of 3 divided by 4. And if you look at what happens when you substitute back into this, you get 7, 4 times our answer here, 5 plus log base 3 of 7. Here, I'm going to move this 27 to the 1/3 out of your way to be able to see. This whole thing's divided by 4, minus 5. That's the exponent. Well, if we were to actually simplify this, these would reduce. So you get 5 plus log base 3 of 7 minus 5. 5 minus 5 gives you just 7 log base 3, 3 of 7. Nope, 7 of 3. So this was correct down here. This should be 7, 3, 7 to 3. This is 7 to the power that it takes to bring 7 to become 3, which is 3. And is it working out? If we look at this next one, we're going to want to get the log by itself first. So we're going to go and add 9 to both sides. So we have 19 equals 6 to the 4x minus 5. And then log base 6 of 19 equals 4x minus 5. Well, similar to the last one, we're just going to add 5 over 5 plus log base 6 of 19 divided by 4 is our x. And we have solved this equation.